Good morning, everybody. Can you guys hear me well? Yes. You guys hear me now?
Yep.
Yeah. Yes. Now that's much better. Nice. Okay. So we wait a couple of minutes till your friends join in. There will not be a quiz in this lecture, but there will be a quiz in next lecture. We had a meeting with the students' representatives, and they gave me some of the problems you guys are facing. But if anybody has any more concerns, maybe or something they would like to share, please feel free to tell me right now. Nothing. So, for example, about the quizzes, any questions about the project, something like that.
Karam already said that we'll discuss all the projects topics today on today's lab. So I believe we will have all the questions after this one.
Hopefully, yes. I was hoping maybe you guys have some other questions, but that's good. So you're going to discuss it with Karam, and yeah, that's going to be nice. No questions about the quizzes? None. Okay, that's nice. That's nice. We wait a little bit more for majority to join, and we start our lecture. Today's lecture is going to be pretty simple, I hope. It's about GANs, so generative adversarial neural networks, and I'm assuming you guys already took something about GANs now? Is that a yes?
Well, we haven't had it in the machine learning course, maybe like self-study only.
Okay, self-studying, right? Gotcha, nice, that's nice. So I was hoping, I don't know, but usually Professor Khan gives like some lectures about it in the end of the course. So, but that's okay. I think it's about time, right? They should be able to join. Yes, certainly. So the overall content of this lecture will be as following. So we will speak about like GANs, we will speak about their applications, we will speak about how they're made, the loss functions that are used for the training, and of course the training process itself, since it's going to be a bit more complicated than what we have seen in basic image classification. We will speak also about some of the variants of GANs, which are here to basically solve some of the problems of GANs, and of course about the application areas of these artificial neural networks. So first we're going to try and participants can now see your application. I'm not sure what that is. Yeah. You guys can see the screen very well?
Yep.
Okay, cool. I don't know, just got some notification. So yeah, so first thing we're going to try and understand what is discrimination part, right? So there are two parts in the GANs. So there is the generative part, there is the adversarial part. Now, GANs are made with one very important architecture, and that is the adversarial learning part. Before we go into the adversarial learning, and this is like the part that I want you guys to keep in mind. So I do not want to introduce you GANs for the sake of generation. I'm trying to introduce it for the sake of adversarial learning, right? So the goal of this lecture is not to help you generate more images, but help you understand how you can leverage adversarial learning to do more things than just image generation. But for now, we're going to speak about GANs in a bit less detail, and that's by speaking about the discriminative part. So discriminating between images, and that is just classifying them into different classes, right? So here, for example, we have a picture of a celebrity, and we feed it into our model, and the model is going to tell us whether this is class A or this is class B. In this case, it's man, woman, something else. Now, a generative model, on the other hand, is trying to generate more data, right? So unlike previously what we had with classification, we take an input sample and we predict its class. Now we're taking some random or latent representation and we're trying to generate the image. Now I'm going to try and stop here and ask you a simple question. Is this a classification task or a regression task?
Regression.
Everybody else agrees with your friend?
Yes.
Nice, that's very nice. So yes, we're trying basically this ability of generating images is kind of a regression task. So here, for example, the image pixels are values that can range from 0 to 255, meaning the space of the output is a continuous space. Now, another concept that we should really cover is the probability distribution, right? There are many models out there that are trying to learn the probability distribution of a data set or of the data. But sadly, since we are working with a distribution of images, nobody really knows how does it look like, right? So you don't really know how to represent it. And for the sake, there are many models that try to mimic this ability, right? So for example, I'm sure you guys have already learned about variational autoencoders with Professor Khan. Is that true?
No.
Yeah, okay, it's okay. So variational autoencoders are very simple models which try to represent or try to mimic sampling from the image distribution by using two steps. The first step is to sample from, normal distribution, and the second one is to map from normal distribution to image. And this is what they try to do. So basically they take, their training basically is they take an image, they try to force this image or to force the encoder to encode this image into some sort of distribution. And from there, they will go and map this latent distribution to the same input image. So this is what variational autoencoders are doing. So variational autoencoders are learning the probability distribution in kind of an explicit way. Other types of models, such as GANs, they're trying to learn this probability distribution, but in a non-explicit way. So for example, here, what if X is an actual image in the training data? At this point, X can be represented at a dimensional vector of 64 by 64 by 3. So if we represent it as like a vector directly like this? Can we just like consider that there is no relationships between this pixel, for example, and this pixel? So we ignore all the spatial information and try to treat it as just a vector and generate it as like a distribution like this, right? Does this work? That was a question. Do you think it will work to just like represent an image as a vector like this and every pixel as a distribution?
No, there should be a spatial relation between.
Yeah, exactly. So we are losing all the information about the spatial relationships between the different pixels. So here, in this lecture, we're going to speak a lot about the probability distributions, but we're not going to be mapping them in reality, right? So we're just going to be speaking about them, but we're not going to be training them or training on them, right? So if we had a lecture about variational autoencoders, we're certainly going to do that, but I think it would be important also to have a lecture about Do you guys? So far, what I see, you guys have not seen, for example, ResNets and all of these different architectures for CNNs, and you have not seen variational autoencoders or autoencoders in general, right? Is that so?
As a course in university, yes.
Yes, I mean as a course in the university. You have not?
Yeah, we didn't have them.
Okay, I think we should certainly have a lecture about these. Probably next lecture, I'm going to change the content of the material. But anyway, so let's say we represented our data set in that fashion, right? So for example, here we have the different samples. And here are, for example, let's imagine that this is the probability distribution of our data set. Here, for example, is images of female actresses with black hair. Let's say here we have female actresses with blonde hair. And this is, let's say, just male actors in general. So we have different peaks in our distribution of images of people who look similar. So this one is, for example, for women with blonde hair. And we have, for example, here, these are like images that do not have, let's say, like a real interpretation for us, and they have like a very low representation. So for example, you see that these images are a bit, like, they're not really realistic, right? So they're generated from a model, I would assume. So what we're trying to do is basically trying to bring as close as possible this probability of the model. So this is the probability of X being generated from the model. We're trying to bring it as close as possible to the real distribution of the data, given the fact that we have no idea how this distribution looks like, right? So in GANs, as we said, we are going to speak about three different parts. So the first one is the generative part, so learning a generative model. The second part is the adversarial part, which is the most or the main goal of this lecture. And of course, the last part is, of course, the networks part, using deep neural networks. So given that we have a set of training examples from an unknown distribution, P of data, this unknown distribution does not like have any mathematical representation that we can comprehend. And we want to model this, we want a model that can basically draw samples from this distribution without mathematically representing it, right? So we have, for example, a normal distribution of 0, 1. We have its probability density function, and we can easily just know how can we sample from these distribution, right? So basically, we just randomly, what is it called? sample from a uniform distribution, and then we make a mapping towards this one. This is how it's usually done. So it's, if we know how the PDF looks like, it's an easy way to do the sampling. But in our case, probability density function of images is a very unknown area that we haven't really went through in mathematics yet. And this is the main problem with modeling such distributions and, of course, generating from them. So the goal from this is that the model should be able to draw samples from this distribution that should be as similar as possible to this distribution.
Should it be P data in the last row?
A model that can, this one?
Yes.
You see, we're not going to model from, we're not going to sample from P data. We're going to sample from P model and force P model to look similar to P data. You see the trick? So we have no idea what P data looks like. We have no way of sampling from P data. What we can do is sample from P model and make sure that P model looks as similar as possible to P data.
Okay.
Okay. So this is basically the trick. Instead of sampling from P data, which is an impossible thing to do, we will see once we go through VAEs why it's impossible to sample from P data. Once we, so what we do is we make another distribution and try to sample from that one, and hoping that this P model would be as close as possible to P data. Of course, this is a very, very difficult task, and majority of the cases there are lots of errors that you would fall in. But if it works, then it would be an easy way to generate new samples. So why do we use these generative, or why do we generate even more data, right? So there are many goals, There are many goals for this one. The first one is the ability, or to analyze our ability to represent and manipulate high dimensional distributions, such as images. They can be used as a tool in reinforcement learning to add more data. They can be used in semi-supervised learning where labeled data is very scarce, and sampling of realistic examples from high dimensional distribution can have many applications, as you guys might know. So some of the applications is to generate more images, so for training. Other applications can be to generate, for example, more information for games. So for us, right, currently you have like a game and there is a map that is kind of being fixed, and you're just walking around this map. But what if you had like a GAN that is generating for you different scenes and different parts of the game as you go on? So just a non-ending game, right? So that's pretty interesting. And these are the different areas where generative models can be used. Another application is image super resolution. So previously we spoke about superpixeling, I hope, with you guys. Did we speak about superpixeling with you guys or with the other courses? I think it was the other courses, yeah. Superpixeling is in image, classification interpretation, right? But this application is called image super resolution. So basically we take an image like this, and then we just, how do we say? We make it much smaller. So we sample from it, we down sample it, right? So we make it a much smaller image, and we try to recreate the original image from that low resolution input. So in this case, for example, you see, this is just the bicubic algorithm. It's pretty easy, but it doesn't really do much. So it's not very similar to this new one, to the original one. We can see that this SRR ResNet is doing a much better job at it, but definitely the GAN is doing the best. And just so you know, this was the results in 2016. The results now are just even better than the truth, right? So the creator of GANs is this person, and he's now a very famous person in the world of deep learning. And how he created it was like a joke with his friend in a pub. And basically the goal was like, what if we put two neural networks against each other and letting them work, right? So letting them improve on each other. So this was the concept that he just made out with it, like he created with his friend as just a joke, and the joke actually worked and gave us this great new field of applications called adversarial learning. So this this idea of putting two neural networks and putting one against the other is called the adversarial learning part, and this is what interests us the most, as I've been saying. Some of the biggest researchers in the world have said that this is the most interesting idea in the last 10 years of machine learning. So before this idea, so all of it was just like, for example, ResNets, you're just creating ResNet residual blocks and stuff. All the other ideas are pretty easy. Even, for example, we spoke about YOLO last lectures, and we've seen that the basic idea is pretty simple, right? So there's no very complicated logic behind that. You could have like created it yourselves, right? So just by imagining our initial model that we have created together, the very basic model that we have made up from scratch, we were able to kind of get the functioning of YOLO pretty easily. And that's why this idea of GANs, and of course the adversarial part of the GANs, is considered to be one of the most interesting ideas that happened in our field. So the components of GANs are mainly two parts, right? So we have a generator function. For now, we're going to call it the generator function. Of course, it's a generator neural network that tries to create real-looking samples, or tries to sample from image distribution, which is called P of data. It cannot sample from P of data, so it tries to sample from P of model and make P of model similar as possible to P of data. And we have a discriminator function that tries to distinguish real from fake examples. So this distinguishing from real of fake examples is what's going to push the generator to do a better job, right? And these both functions are trained against each other or updated in a feedback loop, making each other better at each individual task. So here's the generator. As we have said, it takes either some latent representation or some random noise. It generates some images, and basically the discriminator, so this part, will only look at real images and classify them as real. We'll look at fake images, classify them as fake. So this part is just image classification basic task. Now let's speak about the generator in a bit more detail. So we know that we have the generator, usually represented as G of Z, is a generative neural network and a differentiable function. The input Z, this is our latent space or the random vector, is sampled from some prior distribution. Usually this prior distribution is just random noise between 0 and 1. But in some cases, in more advanced cases, you would like this random noise to be something more interesting, such as a latent space of some kind, or for example, an encoding of certain classes, or some sort of information that you would like to keep, plus some random noise, right? So here we have noise. Here we might have some constraints, right? So for example, we tell it the thing you create should be a blonde Here it should have an age between like 28. Here it should be like in Italy or something like that. So you can represent or you can control this latent representation as much as you want. And the flexibility is endless, right? Now the discriminator part is a bit easier, right? So the discriminator part is something that you've already have been seeing, and it is just a standard classification neural network. It is being trained to differentiate between real and fake images. So real images is our data X, fake images is our data generated from Z, right? So this is the sample that we sampled from our model. And the output, of course, is going to be either something between 0 and 1. 0 means it is fake. 1 means the model believes it is real. So this is the prediction. Now the goal of training these two, what are they called, neural networks, is to reach something known as the Nash equilibrium. So Nash equilibrium is a concept that is taken from game theory, and all it's saying is that we reach some sort of a consensus between the players, where all the players have found a solution to the game. So instead of training as an optimization problem, we're treating this problem as a game between two players, right? So we have no way of saying the goal of this. So yeah, let's come back. So putting these two against each other, there's no like constraint to stopping the training, right? So for us, usually in like image classification, what we could easily do is just see if the accuracy of this one is getting higher, then that's good. But in this case, where we are generating new samples, we really have no idea of when can we stop the training, right? Should we look at the discriminator's accuracy and stop the training once it reaches 99%? Or should we look at the generator results and find some sort of measure between this image and this image? What can we do basically to know that we finished the training? For us, we are going to define this as the Nash equilibrium. This is the point where we stop the training. And this point is represented as a solution to a game that is called the Nash equilibrium, and it is where the local minimum of loss D is reached and the local minimum of loss G is also reached. So we reach a place where, what is it called? The discriminator cannot get any higher accuracy and the generator cannot get lower on his loss. So both of these losses have reached a place of, what is it called? Optimization. So if we remove this one from accuracy and we represent it in loss terms, so both of these losses cannot go down anymore. So if this one changes his weights, it's going to get worse. If this one changes their weights in this direction or this direction, they're also going to get worse. So this is the definition of a Nash equilibrium. If G of Z and D of X have sufficient capacity, then the Nash equilibrium corresponds to the generator draws a sample and the discriminator cannot discriminate between them, i.e. the discrimination ability of X is going to be 1/2 for all X's. Meaning we can potentially understand it as the accuracy of the discriminator is equal to 0.5. Of course, somebody would say that from the start, like as we start the training, the accuracy should be 0.5 because it's random weights. And that is certainly true. So usually the accuracy is going to look like this. So it's going to increase and then decrease and then increase and then decrease and then increase and then decrease. So in these cases, or in here, the discriminator is doing a better job than the generator. And then the generator picks up and then the discriminator learns how to discriminate these new images. The generator learns new tricks. Discriminator learns new tips. The generator learns new tricks, and go on and go forth until like these big changes start to reduce a little bit, right? And basically, hopefully, in the end, they would give you something close to 0.5, and that's when you know that you reached or you are close to the Nash equilibrium. Now, the loss function of GAN, which looks pretty like scary, right? But in reality, it's a very simple loss function. So here we have minimizing and maximizing. One of them is trying to minimize something, and the other is trying to maximize something else. So let's take a look at it. In here, what do we have? We have the mean or the average over x in our data of log of d of x plus the, what is it called? The mean again of log of 1 minus d of g of z. So here we can see that this is influencing two different parts, right? So there are two values in this loss function. So can somebody tell me this error, log of discriminator of x, does it influence the generator? Let's draw it here. Here's the generator function. Takes a latent space. And here is the discriminator function. This is x. It goes directly to the discriminator. Does log of d of x influence the weights of the generator? Can it have any gradients on the generator's weights?
No.
Exactly. So this part is not being used to train the generator. That's good. So this one is only for the discriminator. And the goal of this loss is to push the real values or the real samples to be as close to 1 as possible. So to predict the real values as 1. Now the other loss function, or the other part of the loss function in here, is depending on z. Z is the latent space that is the input of our generator. Now, does this loss influence the generator? Does it have a gradient that can be used to train the generator?
Yes.
Nice. So in this case, another simple question, does this loss have the ability to influence the weights of the discriminator? Again, yes, right, very nice. Now, one of these two is going to maximize this loss and the other is going to minimize it. So before speaking about which one is going to do which, let's look at what this loss is doing. So we're trying to minimize the log of 1 minus the discriminated value of g of z. So hopefully what we're trying to do is push this d of g of z towards 0. And basically 1 minus 0, that would give us the best minimization. Now, can you tell me which one is going to, can you tell me which one is going to try to minimize this one and which one is going to maximize it? Maximizing it, meaning we're going to push this value as high as possible, right?
Discriminator is try to minimize and generator try to maximize.
Maximizing a value. So now let's go back and see, trying to understand the trick. Very nice. So if we try to maximize it, what does it mean? So originally, the discriminator is saying real goes to 1, fake goes to 0. Maximizing that loss with respect to the generator, meaning we are trying to change something in order for fake to be predicted as 1. What does this, so this is what the goal of this loss function is trying to do. Of course, we have the discriminator trying to minimize this one and sending it to, how do we say, trying to send fake towards 0 and real towards 1. And of course, the generator is trying to send fake towards 1. What does this mean? He's trying to change something in his ways such that the fake images would be predicted or discriminated as real images. Now, he cannot influence the weights of D. He cannot change the weights of D. He cannot influence Z, right? So Z is something that is prefixed. The only thing he can change in order to make this result is, of course, his weights and later on the output image that he can create. Meaning, hopefully, this loss would lead to training a generator that is able to generate images from Z that look as real as possible to the discriminator. This is the goal. Now here you will see that there is like a mix-up. So maximizing over D and minimizing over the generator. This is just to make the loss function look prettier, but usually we have like minuses here and minuses here, but it really doesn't matter. So one of them is trying to go in one way, the other is trying to go in the other. One of them is trying to get fake towards 1. This is the generator, and the other is trying to get real towards 0. But for the sake of simplicity, we created this loss function looking like this one. But if we extend it a little bit easier, it would be more interpretable for me at least.
Could I ask a question about the previous slide? So in the first part of summation, we have expected value, or as you said, mean of the P data. So we know the distribution of P data and we can easily calculate the mean value. But what about the second part? There is a distribution that you said we don't know. We cannot mathematically represent it. So how we need to calculate the mean value of this distribution?
Just a very simple mix-up. The fact is we do not know P data. We know PZ. We do not know P data. Now let's just take it a bit slower and understand why we don't know P data. Why we know P data and we don't know the opposite. Why we know PZ and we don't know P data. So P data is the distribution of the data. Do we know it? Of course we do not. It's too hard to represent mathematically. So what we do is we just simply go through the images one by one. So for image in dataset, put the image through this function. Simple, right? So this is what sampling, or this is what the mean over this distribution is. So this is an empirical mean, kind of, right? We're going just through our data set, sample by sample. Now this one, P of Z, is the distribution of the latent space. Remember when I was describing the input of the generator? So this is the generator. The input to the generator, we called it either random noise or some latent space that you control. Meaning this distribution is always in your hands, right? So either it is normal distribution of 0, 1, or it is some sort of noise in here plus latent representation in here. So this is a distribution that you totally control. Okay?
Okay, but could you also say it one more time how we now get the mean value of P data? On which function we let our data go through?
And this one, this is the mean over the data. What does it mean? You simply take all the samples that you have and you send them through this function, and then you take the mean over that. So this is an empirical mean, right?
But discriminator in this case, what it does return? It returns the class?
1 or 0. Yeah, prediction.
Logits.
So it returns 0.9, for example. 0.12. Yeah. It's a probability.
Mm-hmm.
Yes.
We take a log of it and then we take a mean of this distribution.
Over the data, yes.
Okay.
Yeah, certainly. Yep.
Thank you.
It does not have to be a real distribution to, so this way of saying we are sampling from the probability of the data, all we are saying is we're taking an image that is from our training data set.
Could you elaborate the intuition behind this? Why we should multiply these functions or with expected values?
Can you repeat the question? We're multiplying the what?
Expected values and the function that you explained. So it is clear why we use this logs function, both for discriminator and generator, but what is intuition behind expected values multiplying?
So this multiplication.
Yes.
This is not a multiplication. This is a very good question. So in reality, what this is looking like is like this. E of...
I'm sorry.
No, it's okay. That's a very good question. Thank you so much for asking. Log of d of x. So it's E of log of d of x, right? So E is a function. Now in here, usually remember when you have this big sum and you have the index in here, I equals 1 to n. This is the same thing that we have in here. So usually when you say E or the mean of, you try to represent what is your variable in here. P of data, sorry. So this is how it's looking like. And here, log of d of x. Okay? So as we said, we take x, put it through the discriminator, take the logs of these values, and these values we take the, what is it called? Their average. We take their mean. That's it. So it's not like a multiplication in here. It's just an application of the mean to this distribution. Of course, this is not a real distribution or PDF. This is just an empirical distribution that we are getting. Same thing in here. This is not like a separate values. This is just a function or the mean function applied to this formula. But thanks a lot. Thank you so much for this question. So overall, the loss function, this is what it's trying to do, right? So the goal of the discriminator is to distinguish between real and fake images. And the goal of the generator is to create data such that they can fool the discriminator. So depending on what our goal is, we're gonna try to prefer one over the other. So for example, if you are trying to build some sort of a security metric, some sort of a security measure, right? So you train it on these bad samples and you, for the fake samples, and you're trying to make sure that it only has a very high discriminator ability. So you're trying to push the discriminator to have a very large accuracy. And if you're going to use the model for like some generative parts, you're trying to make the accuracy close to 0.5. So depending on what your goal is, you're going to either put this one roll higher or put this roll higher. So here, let's take a look at the data in general. So here we have the probability distribution of the data. Or this is how it's looking like, right? We have the samples. We send the sample through our discriminator. It's a neural network that should give us 1, or should give us something very close to 1. We take Z, so this is the distribution that the data, that the model is trying to arrive at. So if we look at this as the distribution of the data, this is how it's looking like. This is what the model is trying to imitate. So these are the fake samples. And as you can see, over the iterations, the model is going to represent or going to build a distribution as similar as possible to the distribution of the data. So here, what we do is we take a latent space, put it through the neural network, it becomes an image. the image goes through the discriminator. Discriminator should give us something close to 0. So what we're going to do is we're going to adjust basically the weights using backpropagation. Are you all familiar with what backpropagation is?
Yes.
Ah, that's good. That's good. At least that's a good part. Yeah. So the goal of our work is to basically arrive at this point where we have loss equals 0.5, accuracy equals 0.54 are in the middle, right? You can no longer distinguish a real sample from a fake sample. So basically the best case scenario would be if we take some real images here and take some real images here, send them through the discriminator, the accuracy is going to be 0.5. That's what we're trying to imitate here. So even though these are not real images, so these are fake images, we're trying to mimic this scenario where these images look as real as possible to the discriminator. So here we're going to try to understand where is P of Z, P of X, and all of these concepts. Now, again, in our case, we're working with GANs. It's not very difficult to understand these concepts, but if we were working with something a bit more complicated, such as variational autoencoders, things would get a little bit messy. But thank God, we're only studying on GANs, right? So can somebody tell me what is P of data? Just quickly, right? Very quickly. Can you guys hear me? Are you still here?
Yes, it's distribution of the data that we have, so the images.
This one, nice. Can somebody tell me what is distribution of Z?
Initial distribution that we choose some noise that is the input for the generator mode.
Good, so it's normal distribution of 0, 1, for example. Can somebody tell me what is the discriminator over the generated over Z?
It is below's arrow when we
And can somebody tell me what is D of X?
It is upper one when we put
It's the output.
the discriminator.
Good, so it's the output of the discriminator given a real image. So now we're going to speak a little bit about the cross entropy loss. So I'm sure you guys have already studied cross entropy, or no?
Yes,
Professor Khan.
Of course,
Okay,
we studied.
good. So it should be a pretty easy one. So cross entropy loss is a very cool loss that's trying to work with especially classification cases. So let's kind of build this representation ourselves. So here we have different classes, and we have their one-hot encodings, right? So 1, 0, 0, 0, 1, 1, 0, 0, 1, 0, and so on and so forth. So the cross entropy of this one is going to be calculated as follows. So probability P1 of being a dog is equal to 0, P2 of being a dog is equal to 0, P1 of being a dog is equal to 0, P1 of being a horse is equal to 0, P eagle is equal to 0, P squirrel is equal to 0. Now for P2, of course, they're all zeros besides the probability of being a fox. So let's kind of do the math. Let's say we have a sample, let's call it Q1, and this is the probability distribution of its output. Let's calculate the cross entropy between these two. So what we should have is minus the sum over P1 of I multiplied by the log of Q1 of I. So P1 of I in the first one is 1 multiplied by 0.4. So it should give us 0.4. The second one is 0 multiplied by 0.3. So this disappears. 0 multiplied by 0.05. This disappears. 0 multiplied by 0.45 by the log of 0.5 disappears. 0 multiplied by the log of 0.42, sorry, disappears. So in reality, we end up with a value called minus log of 0.4. Only the point of interest is what's going to influence this loss, or the class of interest is what's going to influence this loss. And here we have the minus over, yeah. So you guys know log is looking like this, right? So the log before 1 is always a negative value that is very large. So if you multiply it with a minus, that gives you a very, very large result. So overall, this function should be looking like this. And here's 1. So our goal is to get the prediction as close as possible to this 1 to go down, right? It, of course, cannot go higher than 1. So this is what the loss function looks like. This is what cross entropy does. So it's trying to measure a difference or a distance between one probability distribution to another, but only with regards to, of course, the places of interest, because we are using this one-hot encoding metric. So the cross entropy goes down as the predictions get more and more accurate. It becomes 0 if the prediction is perfect. So in our case, if it was, for example, 1 in here, and of course the others would be zeros. 0 multiplied by zeros, this one disappears, and 1 multiplied by the log of 1, 1 log of 1 gives you 0 multiplied by 1, and it just disappears. So this is the best case scenario. Cross entropy goes down as the predictions go more accurate. Binary cross entropy is like a very small modification of this one. In this case, we have only 2 classes. For example, there are only dogs or cats in this image, or in our case, fake and real. So there are 2 classes. So the cross entropy formula can be simplified as follows, equaling minus probability of cat times log of cat minus probability of dog times log of dog, right? So this is the original cross entropy formula. And of course, I is going through the different classes that we have. So here we have cat, cat, minus dog, dog. This minus, of course, is going through the sum, and it gives us 2 minus values. Using this fellowship relationship, probability of being a dog is equal to 1 minus probability of being a cat. And this is only given to us because we're using, what is it called? Sigmoid activations. So basically, or in our case, for example, softmax, if we have multiple. So the sum over the output of probabilities is always going to be 1. So here we have probability of being a dog is equal to 1 minus probability of being a cat. And we can simplify it. So we just put it in here. It becomes, it becomes, let's write it. Why did he simplify this? So yeah, P is P of cat, and P hat is Q of cat. And in this case, we have minus P log of P hat minus 1 minus P log of 1 minus P hat. So P hat is basically our prediction. P is the probability of being a cat. And this function could be like simplified by taking this as a root as what it goes. So minus P log of P hat minus 1 minus P log of 1 minus P hat. So this should give us our loss function for training the GANs. Remember, it's pretty similar to what we have seen before, but it could be simplified a bit further on. So here we have, yeah. So yeah, this is our model. Sorry, just. Nice. Sorry guys for this delay. I was just fixing up the bureau a little bit. So here, this is the loss. This is the loss function that we have had previously, and we can simplify it even further to get the following, right? So we have the label for the data coming from the true distribution, or the real data, is y equal to 1, and of course the distribution, that is y hat, or the prediction of an image from the distribution data set, is d of x. So this is the output. We're trying to push d of x towards 1, meaning we have this loss or cross entropy loss between 1 towards d of x is equal to log of d of x. To simplify this further, let's just come here and look how does it look like, right? So we have 1, which is what we want, the real label. And here, this is d of x. So we're going to keep it as d of x. So 1 multiplied by log of d of x, it stays. 1 minus 1, this becomes 0 multiplied by something, and this disappears. Now, when we go in the opposite direction and we start working with the fake data has a label of 0. And of course, this is what it looks like. So it's the discriminator over the generated sample that's coming from the latent space Z. And if we return it, or if we replace these values in this function, we should get what follows. 0 multiplied by some value, we don't care what it is, plus 1 minus 0, so this becomes 1, of log of this value. And it could be simplified as follows. So it's the log of 1 minus d of g of z. So basically 1 minus 0 just becomes 1. We can completely remove it and keep only this part. And this part disappears because it's multiplied with 0. So the loss function becomes what we have seen early on in the data. Sorry. Yeah. So here we have our beautiful loss function from before. Now, the objective of the GAN is to basically minimize this loss function or maximize it. Let's see who's going to be minimizing and who's going to be maximizing. So the objective of the discriminator is to correctly classify the fake versus the real. So we need to maximize the previous both cases. So let's just look at it, right? So here we said cross entropy goes down as the predictions get more accurate. So if we want to have a good classifier, we should decrease the cross entropy. But at the same time, cross entropy always comes with like these negative values, whereas now we're taking it in its positive form. So the maximization or the minimization becomes a maximization problem, and we have this beautiful representation. So this is what the goal of the discriminator is. It's to maximize these two cases. Why is we using the maximization again? Because we should have a minus here and the minimization, but since we multiplied it with minus, it becomes a maximization. This is only for the sake of making it more beautiful, right? So in the case of the generator, what we're trying to do is we're trying to maximize the value of d. We're trying to make the discriminator predict predict fake samples as real, or predict them in the same class as the real samples, which is 1. So we're trying to basically minimize this function. Again, if it was a minus in here, this would be maximization, and the other would be minimization. But for the sake of simplicity of the formula, we would use this one as minimization and the other as maximization. So overall, the formula looks like this. Discriminator is trying to maximize this function. The generator is trying to minimize this function. So overall, we can combine it in this horrible formula in here, where this one, log of d of x, here it is, log of 1 minus d of x, d of g of z comes here. And of course, this one is the same as this one, it comes here. This generator is trying to minimize this part. The discriminator is trying to maximize these both parts. And this is the goal of our function. This is only because the author decided to come up with this horrible long formulation of the loss functions. Me personally, I would have liked it this two separate formulations. It's a much easier formulation to look at. But of course, we always love a bit of complicated math. That's nothing. Now, the training of GAN is the final part of our lecture, and we will be speaking about some of the problems of GANs during this training. So the problem in here is that we have two separate neural networks, and we need an algorithm that handles two problems. The first one is GANs must be able to juggle two different kinds of training, so generator training and discriminator training. And GAN convergence is very hard to identify. As we said, we're trying to look for this Nash equilibrium, but there's no function that, or something that tells you have reached the Nash equilibrium. As I told you, a good tip is to have the accuracy equals to 0.5. But the problem is, from the start, accuracy should be randomly close to 0.5. So just 0.5 is not good enough to identify convergence, right? It's not able to identify the Nash equilibrium. So the alternating training is one of the methods that can help us train neural networks. Of course, there are different techniques for training GANs, but what it simply says is the generator and the discriminator will have two training processes, and we will train each one of them iteratively, so alternating. The discriminator trains for one or more epochs, and then the generator trains for one or more epochs, and then we repeat these again and again. This is a hyperparameter, this is a hyperparameter, and playing around with it will give you different results. There are some rules for how many times or how many epochs you should train the discriminator, and there are some rules for how many times you should train the generator. Some people you say that you should have this one as double of this one. Some people say that you should just play with the learning rates and have this one higher than this one. But of course, it depends. You're going to have to play around with these and see what works for your example or for your data set. So the alternate training between two discriminators and the generators would look something like this. So here we have the beautiful discriminator, which is our differentiable model. And here we have the generator, which again, another differentiable model. And what we do is when we are training the discriminator, we block the generator. What does it mean to block something? I think we have done this. I hope we have done this, or it would have been in the other course. But I'm sure you guys have seen in PyTorch how to freeze a couple of layers, right? So for example, self.network. Let's say fully convolutional one dot trainable equals to false. So I'm sure you have already seen such coding, right? Such coding practices when you study about all the transfer learning techniques and stuff. Is this true? In PyTorch, have you frozen some layers before in PyTorch? Transfer learning?
Personally,
Yes,
but
yes.
I heard about it.
Nice. So you heard about it. Nice. That's good. So what we're going to do is simply, while we are training the discriminator, we're going to freeze the weights of the generator. Freezing them meaning we will not calculate the gradients with regards to this loss. And of course, we will not make any step or any change in the values of these weights. So there's no back propagation happening on this boy in here. Now the second part of the training, of course, is the training of the generator. And in this case, we're going to freeze the discriminator and we will train the generator on its loss. So its loss again is trying to make the output of the discriminator coming from this generated sample as close to 1 as possible. So fix the discriminator's weight, sample from this generator, and then backpropagate the error through the weights of the generator without touching the discriminator, right? So the error is going to be backpropagated through the discriminator, but not touching the discriminator, not changing it. Of course, this is how it would look like. Just to confirm, we still have a lot of time, right? Nice. So this is just an algorithm that can be used for the training. This is the discriminator updates. This is the what is it called? The generators updates. And what we simply do is we go through a for loop. Here goes, we sample some noise samples. We sample a mini batch of M examples from the real data set, and then we update the discriminator by ascending its stochastic gradient descent. So this is the update rule for us. And then for the generator, what we're going to do, we're just going to sample from the noise. We're not going to sample from the real data, just noise or from random data. Send the data through the generator and then update the generator's weights through this loss function. Very basic, as you would expect. Of course, there are a few more techniques, let's say, to get this, how do we say, a bit better. I'm hoping to have enough time to go through all the different techniques, because there is a very good link that I wanted to share with you guys. Let me see. Yes, link number 1, link number 2. Very well. So these are two very good links that I really recommend you guys should take a look at, which is called 10 Lessons I Learned Training GANs for 1 year. And of course, here it's tips for training stable generative adversarial networks. This is very good, and it will be in the content of the quiz in the next lecture. So I will highly recommend everybody to read this content. It's very easy, very simple, and it contains some very good lessons about training GANs. This content will certainly be in your next lecture, okay? Or in your next quiz. Next quiz, we're going to have a, what is it called? A quiz, yeah, a quiz about GANs. And hopefully these two references will help you understand more about training GANs. And I'm going to ask questions about those two references. These questions are not covered in this lecture, okay? So one of these tricks would be the modification in the generator's updates. So this idea is simple. So when the sample is likely to be fake, we want to give feedback to the generator using the gradients. However, in this region where d of g of z is close to 0, as you can see, the curve of the loss function is pretty flat. So this is not very, what is it called? It's not very useful for the training, right? So it's not flat enough for the training, or it's not curvy enough, right? So this is very good. It helps the model train faster. This is not very good because the update rule is going to be very small. So the area is very flat around the gradient set to 0. So the trick is, instead of minimizing the likelihood of the discriminator being correct, we would maximize the likelihood of the discriminator being wrong. So this is the opposite of that loss function. So here, this is the loss function that we would get from doing this training. So it's a very simple trick, but it gives you like similar performances, but much faster results. So in effect, the objective remains the same, but the gradient signal becomes much stronger or much faster, right? Because the change in this direction is much bigger than the change in this direction. This is one tip to basically change a little bit in the loss functions definition. It still remains as the same concept, but it gives you a much larger, basically, a much larger training or much larger signal that's going back to the, what is it called? To the generator. So adversarial neural networks have this advantage that they don't need Markov chains. And of course, maybe you have seen this Markov chains being used for different generator techniques. And probably we might speak about these, not in the next lecture because the next lecture is already set, but probably we will speak about it in the next 2 lectures, right? So when we speak about AE, VAE, and all of their friends, we will speak about these concepts. So here we are only using backpropagation technique, which is being used to obtain the gradients. And no inference is required during the training, and wide variety of factors and interactions can easily be incorporated into the model. So again, as we have said, in this latent space that you are generating from the Z, you can add as many parts in here as you want that are fixed, something that you want from the model to generate. There's a lot of flexibility in GANs, and you can use them in lots of areas. Some of the problems of GANs are non-convergence and mode collapse. I'm going to speak about them here pretty quickly, but the goal of this reading is to basically explain to you what these 2 problems are and some of the tips that you can find in training them. Can you guys see this? No, not this. Again, wow. Yeah, now it's working. So yeah, this is the link that I was just showing you, and it's pretty good. So it's going to speak about the stability of the neural networks, early stopping and why it's not good, loss function selection, so what we have spoken about earlier, balancing the discriminator and the generator weight updates, mode collapse and how you can fix it by changing the learning rates, adding noise, label smoothing, setting it to around 0.9 instead of 1, multi-scale gradients, and 2-time scale update rule, and spectral normalization. All of these 10 concepts are pretty useful in the training of any GAN architecture going forward, and not just GANs, also for any adversarial training part you will do in your future, right? So adversarial training is very good for those who are going to be working in what is called in research. So definitely do take a look at those 10 tips and prepare them for the next quiz. But for now, let's speak about only these 2 small tips that we have here. So for non-convergence and for mode collapse, for non-convergence, we'll speak about it again shortly. So deep learning models in general involve just one neural network, right? So there's no maximization and minimization trying to happen. There's no competition. And this player is trying to maximize its reward or minimize its loss. So maximizing its reward in the cases of reinforcement learning, for example, and this one in the other cases. And just using stochastic gradient descent, we're going to try to find the optimal parameters. And stochastic gradient descent has this guarantee to converge under some conditions, of course. And this problem with non-convexity, we might still converge to a local optimum, right? So usually how you guys would usually see the loss functions, right? So something like this. But in the end, you're always going to see this pattern, right? So if we smooth it out, it should be looking like this. This is not going to be the case for GANs. So the problem with GANs is that it involves 2 or more players, and the discriminator, of course, is trying to maximize its reward, whereas the generator is trying to minimize the discriminator's reward. So usually the loss functions are going to lose like this, right? So they're going to look very crazy for you, and you will not be able to find or detect the convergence. So this problem is because stochastic gradient descent was not designed to find the Nash equilibrium for the game. And the problem in general is we might not be able to converge to the Nash equilibrium at all. This is one problem. Some of the fixes are again in the slides or in the references that I just gave you. I haven't sent them in the chat, have I? Yeah, I have not. Let me send them so I don't forget. Worded introduction to computer vision. There we go. Reading for next quiz. Yeah, now let's continue. The next problem is mode collapse. And this is like the easiest thing that you could think of. This problem is very simple. So let's say this one. This is what's expected from the model. This is our target, right? This is what the data looks like. And of course, at the start, the model, the generator is giving us something pretty random. And then it tries to learn, it's learning until it reaches the same distribution of the data as here, right? The problem is he might be stuck on generating the same sample again and again, right? So if the model keeps on generating the same real image again and again, then everything is being correct, like the loss functions are at their optimal operations, right? So there's nothing wrong with what the generator is doing. It's just not useful for us, right? It's just being repeatedly generating the same sample again and again. So it doesn't matter how much we are training, doesn't matter how many times we are training it, doesn't matter how many iterations we leave it, it's always going to be repeating the same loss, the same values or the same image again and again. And that's because the loss function is set to 0 in that image, right? So he found an image, this is the perfect image, and instead of generating a variety of images that look like the training data, he's just generating one image that looks very perfectly like the training data. And this is a very common problem that you see in neural networks or in generators in general. So mode collapse often seems to collapse to far fewer modes than the model can represent. So here, for example, this is our real samples. Oh, sorry. Oh, this one is. Yeah. Ah, yes, sorry. So if we are going to play with multiple parallel generators, and we're going to share parameters up to a certain layer, applies the diversity loss on different generators. So this is just like a simple technique to fix this problem, but we have much more simpler things, right? So alternatively, have D predict which generator the fake sample came from. So this one is, instead of trying to say the loss function is fake or real, now we're going to say, is it real? If it's fake, where did it come from? So this allows the, let's say, the loss function to be a bit different than just real or fake, right? So in this case, if this guy is keeping, let's say he is trying to keep repeating the same image, like he keeps on giving us this perfect image again and again, the discriminator is going to pick up on it. He's going to learn that this is the responsible generator for generating this image again and again, and he's going to penalize it for that. And basically the generator would have to change its output to adapt to this new loss function. So the idea is pretty simple. The idea is to enhance the feedback that is going to the generators. Instead of saying real or fake, now we're saying if it's real, okay, if it's fake, which one generated it. This makes it so if you repeat the same generation again and again, the discriminator would pick up on this problem and would penalize you for it. And of course, if you are penalized, this means you have a high loss function. High loss function means you are going to change your weights, and basically we're not going to be stuck in this small collapse. And this is like one simple fix for it. Again, there are much better fixes or much simpler fixes for this one in the slides that or in the references that I've shown you. And I think this method does provide very good results, but it does come at a very, very high cost for training. So we're going to train a lot of them, and that's pretty difficult, especially in our cases where we're working with, for example, Colab and stuff. It could be a bit difficult, but there are some much easier, let's say, tips in order to evade this one. So this one is pretty simple. All you're doing is improving the feedback to the generators instead of having a simple feedback of true and false, or false, fake, and real. Now we have a feedback of is it real, and if it's fake, who generated it. So some solutions that you can implement is to scale the image pixel values between -1 and 1, use TANH as the output layer for the generator, experiment sampling Z with Gaussian distributions, batch normalization often leads to a stable learning, use pixel shovel and transpose convolutions for upsampling, avoid max pooling for downsampling, use convolution stride. Atom optimizer usually works better than just stochastic gradient descent. And of course, adding noise to the real and generated images before feeding them into the discriminator also helps. Again, this is one list of tips. You have another list of tips on the references that I have sent you. And I'm going to ask questions about, of course, all of them in the next quiz. So definitely be ready. Just some remarks about the lecture. I think we are close to finishing. They currently generate the sharpest images and like they are the state of the art in image generation. They are easier to train than other generative models. They're not easy to train in general, but they're like easier than other models, which are much more complicated because there's no statistical inference required, or there's no real modeling of P of data. We're not modeling, or we're not trying to model P of data, which makes it much easier to work with. And only backpropagation is needed to obtain the gradients. GANs are difficult to optimize, of course, due to their unstable training dynamics and due to this idea of putting two networks against each other. You can find some more tips and tricks in this link. It's pretty also useful. Some active area of research is to have better loss functions that are more stable for the training. So we have this WGAN, we have LSGAN, and definitely many others. And we have the conditional GANs. And we have the conditional GANs and GANs for all kinds of applications. So for example, conditional GANs are something that we should try to speak about. It's just, instead of having a latent space coming from random noise, we have random noise in here and we have some conditions in here, as I said. So for example, this is like age, this is condition being blonde, this is condition on the gender, and you generate images for these conditions. And the discriminator, of course, will have also not just real and fake, but also the classification over these different conditions. So this is what conditional GANs give you, right? You're able to generate images, but with a bit more control. Why to use GANs? So the GAN is nice for many reasons, some of which are listed in here. The design of the generator has very, very few restrictions, meaning you could incorporate anything you want. So you can add CNNs, you can add an LSTM, you can add anything that is trainable. So GANs are pretty flexible with many data types. And the GAN does not require any variational lower bound. So this one again comes from the VAE. Once we reach it, we will speak about it, but this is very, very horrible part about training a VAE. It's because we are not really able to represent the loss function in a mathematical manner. So we're going to use a lower bound. Instead of training on the loss function, we're training on the lower bound of the loss function, which is bad. GANs are asymptomatically consistent, and GANs are subjectively better at generating samples. The sampling or the generation part is pretty straightforward. So we just take random noise, send it through the generator, and there you go, you have a new sample. And training does not involve any type of maximum likelihood estimation, unlike other generative models. It is pretty robust to overfitting since the generator never sees the training data ever. This is something pretty nice. And empirically, GANs are good at capturing the modes of the distribution. Application areas of GANs are image-to-image translation, text-to-image synthesis, face aging, many more things. So this is what image-to-image translation looks like. For example, you take this mask of the road and you try to generate what it would look like in reality. This could be pretty helpful, for example, for self-driving cars to give them a bit more data and of course give them a bit more noise to work with, even if the sensors are not correct. Hopefully the car would still be able to drive, let's say, optimally. Here, for example, we have labels to facade. Here we have like black and white to color images. So we are coloring the images. As you can see, it's pretty good. Here we have edges to photos, day to night. And of course, here we have input. And this is the structure of the buildings. Text to image synthesis would look like this. So for example, this small bird has pink breast and crown and black primaries and secondaries. So now we're trying to generate images from text. This magnificent fellow is almost all black with a red crest and white cheek patch. So here we are generating images. Of course, they're not perfect, but they're still good enough. So this white and yellow flower have thin white petals and a round yellow stamen. So here we go. Not perfect, but these are the results from 2016. Certainly you can imagine now we have much better results. Face aging is the following. So for example, we take an image of Circe and we are trying to change the age of this person, taking a person that's very young, making them very much older. Again, this is what we had in 2017. Now, even with TikTok, you can do something much better than this. And it gives you like very good and accurate face aging models, right? Image inpainting is just ending or finishing up the different images. So honestly, if I wouldn't have looked into this part like in detail and focused on it, I wouldn't know that this is fake, right? Of course, when you focus on it, you can definitely see that this makes no sense in terms of architectural meanings, but overall, the colors and the shapes are looking very similar to the rest of the image that I wouldn't have noticed this as a fake part. Same thing here, for example, looks very realistic. Same thing, for example, here, looks very realistic. Same thing everywhere, right? So this is the results. And again, this was from only 2018. Now we have something that is much better. We can, of course, create new art. And this is just some of the reading that you guys can take a look at. This paper is pretty easy to look at. It's very heavy in mathematics, but it's easy mathematics, right? So it's not like something very difficult. As we said, we do not model any distributions. So overall, the training is pretty easy and the math is pretty simple for this kind of models. Do you guys have any questions about GANs so far? Of course, you have some extra slides that you can take a look at also. Any questions so far about GANs in general?
Yeah, actually about this slide, why convolutional stride is better than max pooling?
This is just some tips that were shown to work. Of course, you're saying convolutional, where is it? Use convolutional stride instead of
avoid max pooling and use convolution stride. So why?
What max pooling does is pretty simple, right? So you take this area and you completely ignore this. You completely ignore this, only take one pixel out of the rest. This is pretty bad for the training of the GANs because we're trying to make the, what are they called? The pixels, every pixel is important. We're trying to make them very coherent with each other. So max pooling would kind of like remove this, some of the information from the images, whereas stride will keep that information at least as much as possible, right? So even if you do not have any intersection between your kernel applications, you are still taking in consideration all the pixels of the image. But when you use max pooling, you only take into consideration one small part of the image and the rest you completely ignore it. So if this part was a good pixel and all of these were bad, we're not going to know why these were bad. Does that answer your question?
Odd-sized kernel size, right?
I did not hear you.
It uses odd-sized kernel, like 3
yes,
or 5.
Yeah.
Okay.
Why not? But did you get why avoid max pooling and use convolutional stride instead?
I just thought that it uses like one-by-one convolution with stride and it simply ignores some pixels. So I didn't
no. Any other questions, maybe? If not, then thank you guys so much. Hopefully on the next lecture, guys, please prepare very well. You're going to have a lot of reading. And yeah, it's going to be an easy reading, but it's going to be pretty useful for you in the quiz. And of course, in your real life. If you guys have any more questions, please feel free to contact me directly. If not, then Karam is probably waiting for you. See you guys.
Goodbye.